Section 29.3, photons and the photoelectric effect. So electromagnetic waves, light, are composed of particle-like entities called photons. So even though we're used to seeing light as a wave, we could break down that wave into individual particles. We'll call photons. And some key equations here. First, the energy of a photon is just given by Planck's constant h times the frequency of the light, E equals hf. So that's worth noting here. We've just plugged in n is equal to 1. And so this is a photon energy, if you ever need to find something related to the energy of a photon. Similarly, the momentum of a photon is given by P is equal to h over lambda. And why is that? Well, the reason is that this is following from our relativistic momentum equation, but with a mass equal to 0. So that's how you can derive it. But we'll just take it as an equation for now, that the momentum is equal. So these are two handy equations that we can use in solving these things. Right, so let's see an example of this. Example 1, photons from a light bulb. In converting electrical energy into light energy, a 60-watt incandescent light bulb operates at about 2.1% efficiency. Assuming that all the light is green light, vacuum wavelength 555 nanometers, determine the number of photons per second given off by the bulb. Right, so a couple of things here. First, they give us the electrical energy of 60 watts. And we remember watts break down to joules per second, because watt is our unit of power, and power is energy over time, so joules per second. That's useful because the problem's asking for a number of photons per second. So that's the first thought. And then it tells us that there's this 2.1% efficiency in creating light energy. So that means of the 60 watts or the 60 joules per second, only 2.1% of them are actually becoming light. Most of it's just getting lost to heat. So we need to use this efficiency to know how much energy is actually light. And then we need to figure out how much energy it takes for the light to be green. So let's take a look at that. So the light energy per second would be the efficiency times the electrical energy per second. So the 60 watts or 60 joules per second times 2.1%, which is 0.021. And that comes to a light energy per second of 1.3 joules per second. This would be the light power rate. Now, what about the fact that it's green light? Well, that tells us that each of the photons of the green light has the energy given by hf. So if you know Planck's constant and the frequency, you can figure out the energy of a single green photon. But here they give us the wavelength. So since they give us the wavelength, we're going to use a relationship between speed, wavelength, and frequency to rewrite the frequency as c divided by lambda, the speed of light divided by the wavelength. Now we can plug in. Planck's constant is given to us. The speed of light is a constant, 3 times 10 to the 8 meters per second. And then that wavelength, 555 times 10 to the negative 9 meters. And so that comes out to an energy of 3.58 times 10 to the negative 19 joules. So to get the number of photons emitted per second, which is what we're trying to ultimately solve for here, we want to take the light energy per second, the rate that we're generating light in total, and divide by the energy of a single photon, that tiny number we just got with the E equals hf equation. So we take 1.3 joules per second and divide by that tiny number, 3.58 times 10 to the negative 19 joules. And that gives us a huge number of photons per second, because each photon is only creating a tiny amount of energy. So to get up to 1.3 joules, we need 3.6 times 10 to the 18 photons every second in order to create this much energy pretty wild. So photons are tiny. You don't carry a ton of energy, but there can be a ton of them at once acting together. Now, how did we come up with this idea of photons? Well, some experimental evidence that light consists of photons came from something known as the photoelectric effect. And that's that if you have two charged metal plates and you shine light on them, just shine a light, then at a certain energy, electrons start to eject from the metal plate and go to the opposite plate. You know, if this is the negative plate and there's an electron there, it's not going to want to hang out by the negative plate. It's going to be attracted to the positive plate. But interestingly, it depended on the frequency of the light. Some light was able to eject the electrons at certain frequencies. As long as it was a high enough frequency, electrons got ejected. But if it was below a critical cutoff frequency, no electrons appeared, even if the light became super, super bright and was super intense. So there's something about the energy of those individual photons that are able to kick off the electrons. And these electrons, since they're generated by photons, are called photoelectrons, which is why we call this the photoelectric effect. So what was observed experimentally here is that when light shines on metal, a photon can give up its energy to an electron within that metal. So the photon is kicking the electron out. The minimum energy required to remove the least strongly held electrons, the electrons that are at the outer edge of the atom that they're ready to leave, is called the work function. So the work function is described here, WO. That's the minimum work or energy needed to eject the electron. And that is related to the photon energy. So this is our incoming photon energy, HF. And then that's equal to this minimum energy needed to just eject an electron. And then if the incoming photon energy is any more than this minimum, then it can go, the extra energy can go into the kinetic energy of the ejected electron, that electron is able to move faster if it's given extra energy. So the way we could show this graphically is, here's a graph of the kinetic energy max of the ejected electron as a function of the light frequency, F. So if we rearrange the equation that we saw on the last slide, we can solve for Ke max, the maximum kinetic energy, and we find that it's equal to the photon energy, HF, minus the work function, WO. What does this mean? Well, as we increase the frequency, there's a linear relationship here where the slope of this line is going to be Planck's constant, h. But we can also go down to the intersection point here where the kinetic energy is 0. So if the kinetic energy is 0, well, in that case, HF has to be equal to the work function. And in this case, where the kinetic energy is 0, we call it the cutoff frequency. So we add a 0 subscript to the frequency. And we find that that cutoff frequency is just related to the work function divided by Planck's constant. And so that is a way that we can calculate the minimum cutoff frequency of how much energy you need to put in, right? The right wavelength or frequency of the photon in order to start kicking off electrons. And this electron will barely be able to move, but it'll be just enough to eject it. And then if you give it any more energy, it'll start going faster and faster. Right, so another example of this, the photoelectric effect for a silver surface. The work function for a silver surface is 4.73 electron volts. Remember, electron volts is another unit of energy, similar to joules. Find the minimum frequency that light must have to eject electrons from the surface. Right. So this is going to relate to what we just saw on the last slide. We're going to take a look at our work function equation with our Ke max, but since we're finding the minimum frequency to eject electrons, we set our Ke max equal to 0. And in that case, this minimum frequency is equal to the work function divided by h. But there's a catch. Because we're working in electron volts and our h is in joules, we need to convert that 4.73 electron volts into joules. The way we can do that is that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, which is just the charge of an electron. Joules is equal to 1 electron volt. So that's not too bad to remember, but you can also look it up. That's given to you on an exam in that sort of circumstance. You can also look up h. Planck's constant is often written in terms of electron volts. And so that's another way you can get around this, is if you just use a different value of h. But here's a place where you really want to pay attention to your units so that it does work out properly. And so we find that the minimum frequency to eject electrons from the silver surface is 1.14 times 10 to the 15 hertz. Now, why do we care about these things? Well, one really cool application of the photoelectric effect is a CCD, charge coupled device. If you're like me, you don't know what that is off just with that saying, but it's what's used in digital cameras. It's how a digital camera can record an image in the absence of film. So what happens is an incident visible photon strikes a pixel that's made of semiconducting silicon, and that can eject an electron, and that electron then gets shifted around, and all the electrons get sent in an analog signal processor as a wave with varying amplitude. Those then can be combined into a digital signal of zeros and ones that can be reconstructed into the image you see, right? Where it can tell you about the intensity of the light, and they can use filters to get the right color. So that's one really cool application of the photoelectric effect. Another one is in your garage door opener or closer. There's what looks like a little laser beam that goes across from one side to the other. It's an infrared light, and it's just send those across. And so it's a beam, and that's creating a current. And so then there's a steady loop in the circuit, and it knows it can close the garage. But if you pass in front of it, there's something there I don't want to close, and it stops in its tracks and backs up the way it came. So there's some cool applications of the photoelectric effect and the fact that light behaves as a photon.